And welcome back, students, to part 2 of homework 5B. And we're starting out here on problem 534. This is a problem that is fairly easy, and you'll recognize that I'm going to draw it for you. They give you a very simple distribution like this, it'll be something like this, and they ask a few questions about it. It's basically just understanding. It'll have like probability of 0.1 and probability of 0.3, something like that. And they're asking for you to figure out how much probability there is between certain outcomes down here. Okay, so we've moved into the continuous probability here. We were in the discrete, now we're in continuous. So this problem problem 534 is fairly easy and straightforward. Same with 535. There was another set of very basic questions. It was uniform distribution. Okay, so this is your uniform distribution. Here's your here's your A. Here's your B. And you're going to try to figure out what the mean is right in the middle here. It's uniform, meaning it's monotonic between A and B, just straight, flat, horizontal. Equal probability of any of these outcomes happening. Okay. And so this is geometry, basically, so I'm not going to spend time on this one. This is like cleansing the palette of probability, these two problems here, 34 and 35. So now we're going to get over to 37, okay? And this is where we did some time last week on statistics. And so we're going to use what we have there, okay? I'm not going to spend a whole lot of time. I think you can follow by example here. For any of you, of course, I did go through it last week, statistics. Hopefully everybody was following what I said, what I tried to help everybody with, that is, okay? So if we draw a normally distributed random variable like this, okay? The properties are that in the ideal data is that you're going to find the mean right in the middle, okay? And in the middle, in ideal data, perfect data, you can have a mean. You'll have the median. We'll also overlay that. Your mode will pretty much be that. Okay. The range, we can think of the range. Okay. So if you think of the range, your low point and your high point are going to be the same distance, pretty close to the same distance from the mean. Okay, so if this is distance A, this is also going to be distance A. Your range isn't going to be very lopsided. It won't have like, for instance, the range on the left-hand side from the mean, it would be down 3 versus up 12. That's very lopsided. I mean that this is very shortened up like this, something like this. Okay. All right. So we draw the mean, the median, the mode. Things are centrally located, or central tendency here, where your results are going to be very close to the mean. And as you get distance, as you get further away from the mean, as you go out the x-axis here, the frequency goes down. These are the probabilities that you're going to get anything out this far. The thin tail. Anybody into marketing? There's a book out there. It's been around since the internet, probably I'd say about 2005-ish maybe. It's called thin tail marketing. All right. And what does that mean? It means on the internet, you can get to the people, you can get this very small lucrative markets here, okay, way out here. It used to be very difficult to get to these people until we got to the internet, as long as they're on the internet, right? Okay, that's a condition that we have to have for them. If you fold the normal distribution over itself by the mean, it's going to overlay itself exactly. It's a mirror image. So for all the points that you have on the left side of the mean, you'll have the same points on the right side of the mean. Something like that. Okay? That's pretty much it. All right. So what we are going to have to use the z-score here, and I will use Excel formula. Now we could go over to the internet at any time. There's probably a table in the book or in the Connect system somewhere. But if I go over to here, okay, and I just do a search on, if I look for a Z table, okay, you don't even have to print these anymore. They're all over the place. They come in a few different flavors. They tell you the same thing. You have to know how to kind of use them a little bit, and it actually kind of shows how they work. All right, let's show this one. So this one, I'm going to go to this one. I think this one worked for me the other day. Yeah, this website just happens to have the negatives. Okay, so it's going to show you negative z-scores. Okay, what does that mean? I'm going to grab this. I'm going to use my Snagit screen grab software, which I can't live without. Control C, come back over to Excel. All right, I'm going to drop that in there. That's how it works. Okay, so we're going to have that. All right. So what we did on Friday is we broke up into groups and we all had 3 different kinds of problems. And the idea there is that this has been normalized data. This is a way to express, to figure out, use the z-score to be able to figure out probabilities and likelihoods and such on normally distributed data, especially close to ideal or ideal data itself. Okay, and this is the negative table. So this is showing what we did on Friday is, this is our native data. Let's say we were looking at 55 degrees, and it was the average temperature on, today is March 28th, I think it is March 28th. You know, what's the average temperature on March 28th? I don't know. I'm going to say something like 55 degrees. And I'm going to say that the standard deviation on that might be something like 5. Okay, so when we've actually figure out, if we have the data, we figure out what the standard deviation is, and we plot it here. If we come over one standard deviation and go up here, it's going to end up on the upper shoulder. If we go out another one, it ends up just about in the middle. And if we go out another standard deviation, so what does that mean? We're down here, three standard deviations is 15. We're down 15 degrees from here, so that's 40 degrees. So the actual reading on the chart is 40. We're down 3 standard deviations of 5, so that's 15 degrees. This would be 10. It's getting a little messy in here, so I don't know how well I can clean this up. I don't know how it decides to group when I write here. Let me clean it up a little bit. Let's get rid of this and get rid of this. Okay, the rest of it's all connected. I can't select it out. Okay, so that's 40. We're 55 minus 15 is 40. 55 minus 10 is, this is 45, and 5 down is 50. Get it? Okay. So these are the markings. We're using our arbitrary measure of 5 degrees. We decided that's a thing. Okay. So we can calculate what the standard deviation is. On ideal data, the first standard deviation ends up on the shoulder, the second one in the midpoint, and then down on when it gets kind of thin down here on a thin tail here, just as it's coming in. So I bring that up because if I draw something on a quiz, or you handed this and say, just show me where the mean is, show me where plus and minus 1, plus and minus 2, and plus and minus 3 standard deviations, you have to kind of know where they are. Okay, just you should know that about numbers. Okay, if you're doing data analytics, I mean, normal distribution is a big chunk of what goes on in especially social sciences of business. All right, so we have these native units. Okay, and what the z-score does is it allows people using all kinds of measurements. Okay, so we had, what did we have? We had temperature, and we had motorcycle helmet weight. Okay, so we have one of the groups had motorcycle helmet weight. All right, let's grab it. Gotta grab it. Trying to do this left-handed is not fun. Let's get it. There we go. Okay, delete it. Redraw that. Okay, so some other group had a normally distributed data, and they might plot it. Looks like something like this. This is the motorcycle helmet. I don't know what we said. 3.4 kilograms was the mean. And we're really good in manufacturing, and so the average that the data varies from the mean, which is our standard deviation. That's why we ever came up with it. We picked was 0.1, pretty high tolerance. All right, it's saying that if we look at the average distance to the mean, 1 standard deviation right here, it's only 0.1 kilogram out, and this is 0.2 kilogram, 0.3. We're just using this as a reticule. It's a grid mark system that we just lay over our normal distribution, and if you have pretty close to ideal data, you're going to be out 1, you're going to be out 2, you're going to be out 3 on either side of them in the places that I mentioned before. And this allows anybody that's doing this to come in here, and we're going to use this one table. We're going to normalize our data to the z-score, and how we do that is, okay, so what this draws, remember that the area underneath the curve, okay, as we move from left to right, the probabilities go up, they peak, and they come down, okay? So the probabilities out on the wings are low. The probabilities close to or out the mean are high, okay? That's going to happen, right? And what we can do is we can think of that the area, we can start talking in terms of, okay, what's the probability that the motorcycle helmet is out of range, okay? That it's below the, and we're just arbitrarily for this problem saying, what's to say that if we have to reject everything that's minus 2 standard deviations and further, or too light, right? So these would be light. These would be light helmets. Weight is down here. This is a low weight over here. This is a high weight over here, right? So as the weight comes down, it says we have to reject everything that's 3.4 kilograms minus 2 times 0.1. Okay, so we have to reject everything that weighs up to and including 3.2 kilograms, right? We have to reject that. Okay, that's a way to look at one of these problems here. Okay, so we need, the reason we turn things into z-scores is the common language between our native units and the z-score is the standard deviation. Okay, and then what we do is we take a point, so we kind of know we're going to use a very coarse problem here. I'm using this kilogram problem here, and we're going to say that this is 3.2 kilograms over here, right? Okay, so we need to reject everything lighter than that, but we need to state it in terms of standard deviation. So if this is the point we decide on, okay, what did we say? The z-score is equal to the point of interest, how far away it is from the mean, okay? We're going to take that distance and we're going to be turning it into how many standard deviations, okay? That's what we have the z-table for. Everything's expressed over here, okay? You take that number, okay, so that's to the 10th, okay? The left-hand side goes to the 10th, and then you can look up the precision up to the 100th place, okay? So we're adding into an area here. So we're going to do, this would be 0.11, okay? What is it? 0.11 what? Well, it's 0.11 standard deviations is what it is, because this is how we calculated it. So let's actually do the calculation here. We would have 3.2 minus 3.4 divided by 0.01, okay? So that is going to be 0.2 divided by 0.1. It gives us our 2 standard deviations, and the world comes back and we're all happy again because we kind of knew that. I picked that point on purpose so things lined up, and we're actually picking the point 2 standard deviations down from the mean and less. So what this table does is, this is a formula, and if you want to go watch it and play with it and break it down into its primitives, okay, have fun, all right? The rest of the world, we just use this, okay? Now, there is a normal distribution formula that does all this beautiful rat's nest inside Excel. It's not that hard of an equation if you're a mathematician or if you really want to challenge yourself for deriving things. It's worth going and taking a look what that really is. It's available. You can just look up the equation on Google. All right, but what it is this has been tabulated. Here we have it as tabulated, and then we can use the norm.dist. Is not good penmanship. My font is horrible right now. Okay, so that's the norm, the normal distribution dist of things, and we're going to go do that. Okay, because we can actually build one of these tables. We can actually build one of these tables really easily. So we could just compute for all the gradations that we have. We're grading this table by tenths. The precision is sufficient at hundredths. The precision in this table says that we can go to a hundredths place. Okay, so let's take a look at what's the probability. This is the cumulative, by the way. There's 2 functions. This is the formula of the cumulative. Okay, so the cumulative, right? So this is the probability up to and equal to 0. Okay, so what happens? Okay, so 0. If we take the entire, second here, it's this up here. Let me move. Can't move that. All right. What we're basically doing is if you ran your entire set of numbers through the Z-score. Z transform is something else. The Z-score, if you ran it through there, okay, I'm kind of sort of going in the wrong direction here, but what happens is if you take your curve, everybody takes their curve and they do this to it, all their points, it ends up, what this does is it translates everything so that your mean ends up at the 0 standard deviation. The difference of your mean from your mean is 0, okay? And then things shoot off to the left and right. This is generally the negative territory. Obviously, it's less than 0. That's 0 like that. And this is the positive territory up here, okay? Okay, so we're down in the negative territory. We're minus. Did I get the minus on there? I didn't get the minus, right? So it should be, this should have been minus right there. 3.2 minus 3.4 is minus. This comes out to minus 2 standard deviations. That gets us into the negative table here. All right. So what is the probability that we have a helmet come out right at the mean? Okay, so it comes out at 3.4 kilograms. So 3.4 minus 3.4 is 0. We're no distance from the mean. What's the probability there? 0.5 and all the zeros you can handle. Okay, so that's 50% on the left and 50% on the right. And that's how the tables are sometimes formed, with understanding that you have this property of the normal distribution. Okay, so what we do is, you notice that we take our point. If we took all our points, or we took our mean minus our means, okay, we basically shifted our entire native data so that it sat over the 0, and then where we have 3.2 kilograms, that's going to end up here as minus 2 sigma. Okay, when we're in the z-score land, we've translated this and scaled it. We scaled it by the standard deviation. We put things in terms of standard deviations over here, so we could translate back and forth. This is like a magic machine here, right? Okay, so we take our native numbers, we throw it through the z-score equation, we come up with this, and we come up with the z-score in here. We find it in the table. And so where's 2? Here's 2 way down here, okay? And it's just 2. It's just 2 standard deviations, 0.000, okay? So the probability, this is cumulative from negative infinity to minus 2 standard deviations. Kind of hard to see there, but it's 2.28 if you really want to get real about it. 2.28, okay? So what does that say? Is if we never make anything too big, but we do make things too small, meaning too light, your motorcycle comes out, that means that 2.28% of our motorcycle helmets come out too light. So our yield would be what? Our yield would be 97.72, no, 99, whatever it is, 97.72, I believe that is. Okay, so that is a standard. We will remember that. It's roughly 97%. If we're only losing the left side. Okay. Now, the thing about it in production is we usually think about things in symmetry here. We usually think about things in symmetry, and we said, listen, the customer is usually going to take plus or minus. It's usually symmetric, plus or minus. They're going to reject anything less than minus 2 sigma, or they're going to reject anything greater than, that's more than 2 sigma above the means. Too heavy could mean that there might have been an internal vacuum space that got filled accidentally. It got punctured during manufacture. It actually filled with material, so it ended up too heavy. A lot of times you can actually track back the error here to things that happened in the assembly line, okay? And if it's too light, it might mean that some of the walls broke. It just became there was big internal cavities of material in there. It became too light, so we've got to reject them in both cases, all right? In one area, purposeful voids were filled. In the other one, areas that were supposed to be filled perhaps ended up not getting filled, so they were voids, too light. Okay, so that happens. If we multiply this by 2, we come up with like basically 4.5. So you're talking about 95.5% yield. Okay, so I just took 100 minus 4.5%. This is just 2.28. I roughed it out. Is equal to 4.5. And so our yield between the goalposts is 95.5%. That's the story of 2 sigma. Okay, excuse me. All right, so I went through this relatively rapidly. I'm going to give myself another 537 down here so I can get another sheet. I am going to copy it. Create a copy right after 37. Right there. Boom. We get ourselves. Went a little bit. Put this over here. Gotta get it back. There we go. Got them in order again. And I'll make this 37B. Okay, so we're actually going to do our work on here. All right, so I still have all this business here. Okay, I cleaned up the sheet again. All right, so now what is our problem with the problem? What is our problem? What is the problem of the homework, that is? Okay, so they give us just a wordy type problem around this. And so some of those properties there, certainly follow up with me. I went through that relatively straightforward. I wanted to show you the steps, but it might have been too quick. You can go over it again. And I can also offer some other YouTubes that I've created or other ones that are out there. Okay, so what do they tell us here? In determining automobile mileage ratings, it was found that the mile per gallon is normally distributed with a mean of 39 miles per gallon, standard deviation of 2.1. Okay. It's a good idea to always draw this. The more you draw it, the more it gets actually burned into your cranium. And we have 39, and it says, let's draw our -1, -2, -3. -1, -2, -3, or +1, +1, 2, +3. All right. Okay. So it's going to do. It does pay to play with the data instead of trying to jam on an answer for something like this. It is good to actually lay this out a little bit because you can see there's a graphics involved with this that can help and whatever. So we have 39. We have 39 is our mean, and we have 2.1 mile per gallon is our standard deviation. Okay. So what are the points on this curve that relate to 2.1 as a standard deviation at -1, 2, and 3. So what we're going to do is go equals 39 minus, I'm actually going to do this the long way, -1 times standard deviation. This way I can speed it up. So 39 minus 2.1 is 36.9. That's the first one, see? You really want to know what these numbers are because you're dealing with real life problems here. Okay, so you don't want to get away from what's going on. Here's 36.9. Okay, you get the idea here. So then I can just say we can F4 that. We can F4 that. Okay, we need to F4 both of those. And then when I copy it down, we should get 2 of the same answers there, which we do. And I can just run right in there and change this to how far down are we when we're 2 standard deviations? And how far are we down when we are 3 standard deviations? There we go. Okay. Likewise, I'm going to take this and I am going to copy it exactly. Whoops, Control Z. Escape. Let me do that one more time. Control C and escape. Hit up here. Control V, Control V, Control V. Okay, so I'm just going to fix these equations up here. What we're trying to do is get the points that are above the mean that correspond to 1, 2, and 3 standard deviations up there. And change this to a plus. Okay, oops, to a plus. All right. Save myself a little time here, and then change this to 3. Oops, didn't work. Something happened. One more time, delete 3. And we'll try 2 on that one. Delete 2. Okay, so going upwards, as you would imagine, 39 plus 1 times T6. Yeah, okay, I just want to make sure that's right. Okay, so they look right? Okay, I just want to double check. They looked right? All right, so what we just did is we just figured out how tight our data is by using native numbers here, right? So this is 41.1. Okay, just to get an idea, these numbers correlate to the places on the x that correlate with the plus and minus 1, 2, and 3 standard deviations. All right, so the first question they ask is, find the probability that x is less than 38, okay? So they're getting in pretty close here. So I drew this kind of small, but they're saying, what's the probability you bought one of these cars and your mileage is less than 38, okay? So this is one-tailed, okay? It's one-tailed. It says the probability that you're in this part, we'll kind of color this in, all right? See that? Really close, that 39. So we need to know from 39 to 38, I'm going to clean it up. Okay, from 39 to 38, how many standard deviations is that? All right, so we're going to look this up. The z-score is going to be equal to 38 minus 39 over 2.1. Okay, so how many standard deviations is that? And I am going to equals 38 minus 39 over standard deviation, and I have to go back and just put in the opening paren. Okay, so we're down about a half of a standard deviation. Okay, see, that's why we laid out where the standard deviations were in native terms here, native units here. All right, so we're only about a half of the way down, barely, not quite half the way down. So we can go to the table. We have our negative table up here, and we need 0.47. There's minus 0.4, and we need to go across. It's the white one here, 7 here. Okay, so the probability should be less than 50, thinking about this, right? Because the probability all the way up to the mean is only 50%. And then the rest of it is also 50%. 50 and 50 is 100, okay? So it should come out. You want to make sure you're looking in the right place here. Let me get rid of this guy. I don't know why he popped up. All right. So I don't know if you can read it, but it's it's like 0.139. Okay. Let's see if we got that one right. They came up with 0.317. Not sure why they. Oh, I know why. Okay. not quite sure why they did that. 0.47. 3170. Okay, so now we'll do equals the norm dot dist. Okay, so it wants to know what number is 38. Okay, so it wants to know what point of interest we're talking about. Where's the mean? There's the mean. Okay, what's the standard deviation? Right there. Okay, and the last term is we want to throw the switch to true. Okay, that we want the cumulative versus what you would think of like maybe the spot check of at exactly that point. What we're interested in is everything from minus infinity up to that point. Okay, and indeed, that's kind of interesting. And I don't know what the table is up to here. 4, 8. Okay, because they interpolate. If we interpolate between these, that's why we're not getting precisely that if we have a few more digits on there. So anyway, it's 0.317. That's what they got. So otherwise, you'd have to interpolate. We're a little bit less than 47. You'd have to interpolate on the table here. That's extra work, right? Anyway, so we got a nice. That's why we use Excel. We got a nice precise number there. So that's that one. We got that one. All right. So what's the probability that the mileage is between 35 and 43? Okay. So that way we just have to do two different ones. We need to do two of these. Okay. So first we have to look at 39, and it wants to know between 35 and 43, and that just happens to be plus and minus 4. Okay. So plus and minus 4, that's 35. 4 down, 4 up is 43. So you notice why they picked their points there. Okay. So what we need to do is we want the middle area in here. We want the middle area in here. So we have to get, what we're going to do is we're going to get all the way up to here. We're going to figure it out for this and then subtract the number for this to get the difference, this area in between. Okay, that's all you really need to do there. I'll do one more of these. I'm not really. Okay, so it would be like equal to the point of interest was 35, and I'm just going to type it in this time, and divide by 2.1. In fact, we don't want to do that because we have to interpolate, so we're just going to do the norm dot dist formula. The x is going to be 35, the mean is 39. I'm just going to type it in there, and 2.1 because I'm lazy, and true. Okay. Okay, so that's that. Okay, so the probability is 2%. Okay, it's only 2% of the curve fits to the left of 35 miles per gallon. Now we're going to do the other one. I'm going to do it above it because we're going to subtract it. Equals norm dist of 43, 39, 2.1, true. Okay, true. Okay, so 97% of the curve at 43 miles per gallon, 97% of the curve fits to the left. Okay, but we're going to take the difference. It's going to be equal to that minus that, and we get 94%. And what did we come up with? Yay, same thing. Okay, very good. Okay, so then find. Okay, so now I'm not going to go through the rest of these because you can see what I'm doing here. You just have to play geometry with these. It really comes down to a game of geometry. If you do it a few times, it becomes a skill. You can throw out any problem that is normally distributed here. So again, so how would you do the probability of x greater than 45? So 45 would be kind of way out here. We're getting into the thin tail here, right? Okay. So remember, like in the previous video, we were interested in this over here. So what we have to do is we have to figure it out for 45. Okay. What's the probability up to and including it? The mile per gallon is 45, and then take 1 minus that. So we're going to go to the table and then subtract that from 1. It's going to be a very small number. It's going to be, let's see, we're already out. It's getting out there. It's probably going to be, 0, 0 something. It's not very many. Not very many cars by accident get really super high mileage. Okay. And then they did the same thing here again. They said, what's the probability greater than 38? Remember, we did less than 38. Now they're going to do greater than 38. So you have to go through the same thing again and find the mileage rating that the upper 13% of cars achieve. Okay, I want to make sure that you have a little fun with this, but I will give you the hint on that. Okay, so what does that mean? I hope I can draw on top of this. All right, so here's our curve, like that. Rough it out. It's saying what percentage, is that what it's asking here? Find the mileage, 13%. Okay, so they're trying to find what mileage corresponds to that and above is 13% of the production. Okay, so you're trying to find out what that number is. You just have to reverse the process here. Okay, and it's going to be just a little geometry trick. You have to pick up in the table correctly. All right, yeah, and so you don't need the tables. I just wanted to show you what it is. So you're using the norm.dist function. Okay, and there you go. I'm going to leave this problem there with you. You should be able to get through that between this and what the book tells us. Okay, so we're still in normal distribution here, and it's always a good idea to draw out the image of what you're looking at. Okay, so we have normal distribution, and on this we're doing soda or pop as they call it out in Western New York. All right, our mean, it's supposed to be the mean in the middle, and that's 1,000 milliliters, right? And we have the standard deviation is pretty tight here, you see. On the shoulders, plus or minus 1. In the middle is plus or minus 2. And out at the tail is plus or minus 3. Okay? And it's only 17 milliliters down from the mean and up by 17 milliliters. Not a lot there, okay? So this is probably a process control type of thought process here. If the process fills the bottle by more than 27 milliliters, okay, so just to keep an eye on what 27 means, because we're talking in terms of standard deviations, 2 standard deviations is going to be out there at 34 milliliters. So 27 is going to be between 1 and 2 standard deviations above the mean, okay? So what's the probability of that occurring, okay? This is relatively direct. Z is equal to our point of interest, how far away it is from our mean, divided by the standard deviation. Really fast problem here. I think they actually had this rated as fairly easy, as long as you know what you're doing, but here's our chance to learn. So equals the norm dot dist of x is going to be, it's going to be 1,000, just so we remember how we did this, plus 7, nope, 27 rather, 27. Okay, so 1,027 milliliters. The mean is 1,000. Standard deviation of, you said 17 on this? Yeah, 17. And cumulative. Okay. Now remember that we're looking at the right tail here. Okay, so we're looking at what percentage of these is going to be above 30. Was it above 27? If the process fills about more than 27 liters, the overflow will cause a machine malfunction. What's the problem? So what we want to do is find what's the percentage up here in the upper tail above 27. I could use a different color in there for some reason. My color went away. Okay. All right. So 27 is the line right here. Okay. Above here, it gets damaged. All right, so how many standard, we need to go figure that out. Z is equal to 27. Okay, it's going to be x of I. It's going to be 11. 27 minus the mean is going to be 27 milliliters divided by 17 is going to be your numbers of sigma. Okay, so we don't exactly need that, but that's going to be the number. That's a Z score. Okay, so we just figured out the Z score. All right, but we're going to run equals norm dist 1,000 plus 27. Standard deviation 17 by true. All right, there we go. Okay, so it's the area of the curve to the left is that 94.39. Okay, so the area all the way from minus infinity up to our point here, we're interested in the rest of this, so we would take 1 minus that. So equals 1 minus that. So it's 5%, 5.61% probability of this occurring. Get that out of there. Yep, 0.56. Pretty good. Okay, what's the probability of underfilling the bottle by at least 15 milliliters? Okay, these are sort of straightforward items. I won't go through the graphic part of it. Equals norm dot dist, and it's going to be 1,000 minus what did it say? 15, right? 15. So about 18.9%. Let's just double check, make sure we got the right answer. Did it? That's what we got. All right, that's all we need for 539. And when we take a look at problem 541, I think it's pretty much the same problem as we just had. Oh, it's a little bit different, actually. No, it is different. All right, so let's take a look at this. Draw our customary normal distribution curve. Make sure we know what we're talking about. What's the mean? $20 of spending a month. Standard deviation, so it's plus 4, plus another 4, plus another 4, minus a 4, minus another 4, minus another 4, okay? So that's plus and minus 1, 2, and 3 standard deviations. All right. That gives us a little bit of an idea when they say probability will spend at least 16. So 20 minus 4 is 16. So they're saying how much is somebody in your spending group from -1 standard deviation out to the right. Okay. So the way that we would do that is we understand that this is 16. All right. So we'll go right to the equation, the normal dot dist. All right. It wants to know what point are we interested? Point of interest is 16. What's our mean? Is 20. What's our standard deviation? Is 4. And we want to use the cumulative, which is true. Okay. So it says this 15 is good enough. Okay. So what we calculated here was up to 16 here. All right. And we need to take 1 minus that equals 1 minus that is equal to 84%. Those spend at least. Right? There's our 84 right there. Good. All right. That worked out. Now this problem is a little bit different. Okay. I think, so we need 11%. Normally what you would do is if you're not using Excel and you're using the table. So you have this table. This is in tenths and this is in hundredths here. Okay. These are your sigmas as you go down. All right. And what happens is when you come into the table with your numbers of sigmas, number of standard deviations, you're going to pull out a probability out of here. Okay, you're going to get a probability. Here we'd go into the table, we would find where 0.1100 would be in the table, and then we would look out here on the edge. We'd figure out what standard deviations would be equal to. Okay, so we would have this as a given. Okay, basically going into the equation, and it says what relates to 11%, and this is what we have to figure out. And we have the mean, and we have the standard deviation. And I beg your pardon because really I want to use a z there. Okay, not a sigma. You know, a z is similar to a sigma, so z. We would have that given now. All right, we'll figure that out. We need to figure this out. And so all we do is solve for x of I. So x of I would be equal to your z times sigma plus your mean. Okay, I just moved everything around. And that's how you'd normally figure this out. That's how you'd figure out your x of I. Now, we would use, let's try the normal dot inverse. Okay, and what's the probability? Okay, I think we got it here. So the normal inverse, the inverse of the normal is give me a probability of 0.1. All right, I'm reading back up at the top here to make sure we're doing this right. The mean is 20 and it wants the standard deviation. Okay, so what this relates to, we have to understand, remember, this is going to relate to, there's 16, just shy of 16. Down here is 15.09, blah, blah, blah. All right. So this part of the curve up to 15, this much of the curve down here is equal to 11%. And so we kind of used the behavior of the z-score and inverse. We got this in the normal distribution here, but we need to know symmetrically on the other side of 20, we need this 11%. So the way that we would get that would be 20. See how far away 15 is, okay? Okay, I'm going to use the actual cell value for that, okay? How far away is that? I'm going to calculate it right here. So how far away is that number? And that's how far away it is. That's how far above we need to go up here. We have to add that up to make it symmetric. We need the upper end of this. So it's going to be equal to 20 plus that number. And there you go. Anybody that spends $24.90 or more is in the 11% club. Okay. Yay, we did it right. Okay. Very good. On to the next one. Okay, so this is where we have an exponential distribution problem, okay? And I just pulled the part out of the book that describes it, okay? So you should be getting used to the fact that there's usually these two formula that come along with these distributions. The point formula, okay? So the formula for any specific point on the x-axis is the density function when you're talking about the continuous realm. Okay, so what is our problem here? 24 minutes is our mean. We know this is an exponentially distributed problem because we're told so. And they want to find out, or we want to find out, what's the probability of deliveries greater than 28 minutes? Okay, so this is one of those problems where, so common, we're getting used to this. There's usually a left and a right part of the problem. And they're interested in, after 28 minutes here, after 28 minutes, what's the probability here? Well, we have to use the exponential function to say up to and including 28 and then take 1 minus. Okay, so let's punch in our, I think we have everything we need. Yeah, we could do this, exponential. All right, and now it needs an x, so that's our 28. What's our point of interest? 28. What's our lambda? So lambda is an arrival rate versus the time. We have the time, but you have to use lambda, which is an arrival rate, which is just 1 over the time. Every 1/24th, 1 over 24 is our arrival rate. And then finally, true. We want cumulative there. Okay. So it's 68 and some odd % probability that it's up to and including 28, which, by the way, is going to answer our part B here. Same kind of problem. But we need to take 1 minus that. So 1 minus this. Take 1 minus this. And we get our, oh, if I had only by an equal sign. 1 minus. There we go. So 31% and some change. 31 and change up here. Okay. 31% chance it's going to take longer than 28. Proportion of deliveries that will be completed within 20 minutes. We just already did that basically, right? So it's going to be exponent dot, there's that equals again. Right? The x is 20. Our lambda is 1 over 24. And we want cumulative. Probability, 56. Got it. Got that one down. Not that hard. If you'll notice, if I dare bring your attention to this, these types of problems are somewhat of what you would call like survey questions. Okay, so as we go forward and there's more of these problems through the different chapters, get a feel for what they're kind of asking for. They want you to go execute what they told you in the text. They're going to give you an example. You should be pretty much able to figure it out from examples what are going on. And look, everything's about this symmetry kind of business. Where we're talking about, a probability up to and including a point, and then we end up taking 1 minus that if we need the right-hand side. You can see the pattern through this whole part of the chapter, okay? So this is a bit of a, take this as a lesson for other things that are coming up. If you you might be able to pick up your speed a little bit if you start understanding what the book is asking for, okay? We're beginning to see this pattern here. It's a bit of a, as I say, survey questions. It doesn't take deep thought, and if you've got this, then you're going to be pretty good, okay? Onward to the next one. Okay, and on to problem 544. This is relatively involved, so I'm going to break this off because this video is going on. It's gone on for quite a while, but I'm teed this thing up by grabbing the data out of problem 544, and I've put it in here, but I put a little header up here that this is a service time from a service company, let's see, an airport service times. Whatever that means. Okay, I didn't really get into it. I'm going to break that off into video 3. We'll catch you there. Bye now.